especially in quantum mechanics. If you do quantum mechanics 101, you know Hermite polynomials are very, very important to the harmonic oscillators. One way of defining the Hermite polynomial is in terms of the so-called exponential generating function. And this is not the standard definition. I made a slight change of variable to make the combinatorics and more natural. So it's either a theorem, if you define the Hermite polynomials by another way, or it could be used as definition. It's e to the t plus z t squared, x over 2. So now in Maple, you can use it very easy to crank out the first 100 terms. You go to Maple, you do x at t plus x times t squared over 2, and then you do Taylor, t0, I don't know, 30, let's say. And then you extract the coefficients in t, multiply by n factorial, and you get the first 30 terms of the Hermite polynomials. So this could be used as definition, or it's a theorem, not too hard to prove by boring analytical methods. But when Dominique saw this, he saw combinatorics. This is a famous, beautiful theorem called the exponential formula in the Enumerative Combinatorics. So let me sidetrack and tell you how to about it. Let me give you a crash course in Enumerative Combinatorics of labeled objects. It's really beautiful theorem, but not very hard to prove. So many things in combinatorics are labeled. They're easier to count than unlabeled. Labeled graphs are not that easy to count, but much easier than unlabeled graphs. So you have a combinatorial objects of labels, for example, boys and girls. And suppose that there is some combinatorial structure with boys counted by a sub n. So the number of ways of the number of objects, of boy objects with n labels is a sub n. Now suppose you want to have a co-ed object. You have to have both boys and girls. And you are free to pick the labels. So you have girl objects. And now you want to find a new object combined, co-ed. So you have n atoms, n entities. You first have to decide which of the labels, and you have k boys. You decide how many boys, and the remaining are girls. But this is labeled. You have to decide what labels go to the boys, and the remaining labels go to the girls. So k labels should go to the boys. So the number of ways of choosing of the out of the possible n labels, 1 through n, k labels will go to the boys. Is this? But I'm sure you all know that n choose k is n factorial over k factorial n minus k factorial. Divide both sides by n factorial. So we have this. Now take the generating function. Exercise for you. You get exactly, if you call this capital A of t and this exponential generating function capital B of t, the exponential generating function for the co-ed objects is simply the product. This is the first step. That if you have, you order them. First the boys and then the girls. And what if you have boys, girls, and another gender? Then you have A times B times C. So you have any sequence. But now suppose that I know there are boys and boys and boys. So that you have sets of boys and set of boys. So A plus B. Then you have this. pairs of A and A. But since they are labeled, it doesn't matter which way it goes. So you can really divide by this, and you have 3 components. Divide by this. So if A of t is counting something connected, if you make it into sets, you have sigma. So if A of t is a conventional function for the atomic objects, for the connected components, this argument proves, and this is simply the exponential formula. So to get from labeled objects of connected objects to non-necessarily connected, you get this. And going back to this, I guess. Oops, what happened to this? I guess I So let's put again the generating function for the heavenly two polynomials. So Dominique saw combinatorics. The sigma a sub n x of n factorial times t to the power n. N goes from 0 to infinity equals e to the power t plus n t square times x over 2. That's it. That's one way to define. Once again, it's a normalized. It's not exactly the one from the textbook, but it's equivalent. Okay. Then the exponential generating function. T of one object or two objects. So it's either one, so the atomic object is one, or a pair. 1, 2. So that's the connected component. Very, very simple. The expansion and half. So it's either a single. Now take n labels. 1, 2, for example, 3, 4, 5, 6. So the connected components are either singleton. So it's what's called not necessarily perfect matchings, imperfect matchings. So you make friendships. 5 and 6 are roommates, 2 and 4 roommates, and 1 and 3 have single rooms. So you go to conference, sometimes people like to share rooms, some people like to be on their own. So that's, if you have n people, that's exactly the exponential generating function for these objects in perfect matchings. You take n objects, n people, and some of them share rooms, some don't, so that's one of the many things. Of course, they could be all be spoiled and unsocial. 1, 2, 3. And instead of having a single room, that's one of the possibilities. Or they could all be friendly or cheap and don't want to waste time. So perfect matching are allowed. But that's exactly the exponential generating function. Now, a famous theorem in analysis whose only proofs were very complicated and very ugly was the Mendel formula. And Marco Zeilberger suggested to Dominique Foata in the 1977 to try to find a proof of this. And the beauty of this, so it's a generating function for this. Now you have two variables, x and y. And it's also important for many application analysis. I don't know why, but it is considered important. It's called the Mendel formula. It was an important theorem in analysis. And it had a proof, but a very ugly proof. And the proof was you can express it explicitly. And I don't remember it, but if I have time permitting, I reconstruct it from scratch using Dominique Foata, using the combinatorial framework. So now you have A's and X, then X and Y. So you need two colors, that's why I brought colored chalk. The X color and the Y color. So this is X, and then that's a possibility. And let's make up more. 7, 8, And that's a possibility. So now you have bicolored things. In the original one, every vertex has either degree 0 or degree 1. If it's a singleton, it's degree 0. If it belongs to a pair, it's degree 1. But now that we have these colored things, every vertex has either degree 0, degree 1, and degree 2. So let's analyze the connected components. So we want to find the connected components of these new objects, the bicolored ones. And the connected components are not that hard to analyze. First, we have the singleton as before. So it's possible that it doesn't belong to any pair, not. So this is a T. That's the other possibility. Sorry, that's the other possibility. But then let's look at all the possibilities. It could be white, yellow, white, yellow, and so on. So that's one possibility. So white, yellow, white, yellow, white, yellow, white. So you have K whites and K plus 1 yellows, right? No, K plus 1 whites. You have 1 more whites and K plus 1, K yellows. Then you have the other possibility, yellow, white, yellow, white, yellow, white. Yellow, white, and so on. And then you also have, you can go in circle. So you can have the cycle, white. So you have K whites and K yellow. Did I miss anything? Yeah, that's it, right? Did I miss anything?
Couldn't you have half and an even number of
Infinite? No.
No, even.
Oh, even. Oh, yeah. Sorry. Even. No, yeah, super neat. That's why they have an odd length. Sorry. I forgot. Thank you. Yeah. So yeah, so in this case, could be even, right? Yeah. Thank you. I know. Thank you. Yeah, that's even. Yeah. So here we have K white and K. And it's the same. Yellow, white, is the same. If you do it backwards, but it's the same. Now find the exponential generating function for each of these. It's just summing, easy summing. So here we have K plus 1. So you have to put labels. There are 2K plus 1 factorial ways of putting, and here the end, by the column by symmetry, it's over 2. So the exponential function of this, only of this component, is 2K plus 1. Sorry. Yeah, but now it's weighted. The white is x, the yellow is y. So it's x to the power k plus 1, that's y to the power k, each individual k. So the exponential generating function for this type of connected component is sigma. K goes from 0 to infinity. But there's an exponential generating function. So we have this. The factorials cancel out. And we have a nice simple geometric series we can sum explicitly. And similarly, we can do it for this and get explicit rational functions for this. Finally, for this, you have the weight is t to the power 2k over 2k factorial, x to the power k, y to the power k. But now it's circular. So it's 2k minus 1 factorial. Cancel out. And this is ln of something. And if you exponentiate it, you get something. So I don't have time to do the details, but homework for you. Please reconstruct it. Lots of fun. So you get e of ln something, and then the rest is x of the sum of simple geometric series. So you can get a beautiful, explicit, motivated proof from scratch of this. And I'm sure that this has lots of potential, especially with computers. Humans can go so far, but we need humans like Foata to give nice ideas. And maybe with computers you can get much more mileage out of this. For example, what this is a challenge for you. If you have something like this. Then it gets much more complicated, but maybe still you can do something. So I think that Dominique Foata really contributed so much to modern combinatorics. Happy birthday, Dominique. Thank you very much. Thank you for coming. Reminding you, the OIS conference is